Hello, I'm Justin Mason. I'm a principal software engineer at iStreamPlanet on our live transcoding platform. Today I'm going to give a talk about highly available live encoding on Kubernetes, iStreamPlanet's journey to being cloud native. So what I'm going to cover today is who iStreamPlanet is, where we started a few years ago, and some platform goals that we outlined when it came time to build a new live transcoding platform. I'll cover the architecture that we designed for this platform. And then lastly, I'll cover the outcomes that we've been able to achieve with this encoding platform. So who is iStreamPlanet? We are an over-the-top video streaming provider. Our streaming platform provides our customers source acquisition, transcoding, packaging, and originating of live content for various devices. While there are many pieces and services that make up the streaming platform, we'll just be focusing on the live transcoding portion today. We deliver premium live events for some of the world's biggest sporting brands, from the Tokyo 2020 Olympics to March Madness, the Super Bowl, Premier League, Formula One, and many other international events. These live events have millions of viewers, and so downtime is not acceptable. So let's take a look at where we started and how we used to operate a few years back. At the time, our streaming platform that we built ran on expensive physical hardware, requiring teams of systems engineers and operations personnel to maintain. Upgrades to new software releases took weeks to roll out and were deployed quarterly because upgrades resulted in significant downtime. System failures often didn't heal automatically and required manual intervention, which led to longer customer impact. So for the new platform that we were designing, we decided to set out a series of goals that we wanted to achieve. First was premium quality and feature set. All content is professional and premium quality. Our customers and their customers expect premium quality and premium features. So not just video at scale, but high quality, high frame rate video with SCTE-35, ad insertion, trick play, audio normalization, Dolby transcoding, source redundancy, etc. Second was agility. We wanted to perform software upgrades during business hours, not during overnight maintenances. This is especially critical with a global customer base. There's never a safe time to deploy. Third was scale. The platform needed to run thousands of 24/7 live linear channels at all times, run tens of thousands of live events each year, all while automatically scaling up and down to meet the demands of the changing workloads. Fourth was availability. The transcoding platform needed to be resilient to transient source feed, networking, and dependency failure. Rapid automated recovery from hardware and infrastructure failure was a must. Even small interruptions are unacceptable during premier events. Before we get into the architecture, I wanted to define a few terms that you'll hear throughout the remainder of the presentation. Some of these terms are overloaded and could mean very different things depending on the context. A source is a redundant MPEG-2 TS feed for a given broadcast or linear station. These are set up and managed by our source acquisition team. A channel is a platform resource comprising source, live transcoder, packaging, and publishing. You can think of a channel as TNT or HBO West, or an event like the Monaco Grand Prix. A cluster in the context of this talk is a Kubernetes cluster deployed on AWS EKS, Elastic Kubernetes Service. And lastly, SRT is a reliable UDP transport designed for streaming video over unpredictable networks. With that, let's walk through some of the architectural components and how they work to achieve the goals outlined. We will start with the smaller building blocks and work our way up. The first and smallest component is the live transcoder pod. It is comprised of 4 containers, 2 SRT to MPEG-2 TS translation containers, one for primary and one for secondary, 1 C++ lib transcoder container that performs the heavy lifting of transcoding audio and video from the input source to the configured output ABR ladder, 1 Go transcoder service container where the bulk of the live transcoder's features are implemented, It's responsible for MPEG-2 TS demuxing of source received from the SRT containers, in-source or programmatic API, SCTE-35 processing, feeding input media samples to and processing transcoded output samples from the libtranscoder container, and performing ad hoc video slate insertion, among many others. Here we can see the flow of data through the live transcoder pod. First, source is received over SRT to the two SRT translation containers. Second, MPEG-2 TS is then fed to the transcoder service, where both primary and secondary feeds are demuxed, and the transcoder service decides which feed will be forwarded along to the transcoder container. libtranscoder sends the received input frames through its media processing pipelines and output frames based on the configured AVR ladder. And fourth, the transcoder service collects output frames into GOPs, then GOPs into segments, typically 4 or 6 seconds in duration, and sends those segments to the packaging service along with attached metadata. This containerized architecture provides us with several benefits. First, application dependencies are isolated to the containers that actually need them and baked into their respective images. Second, unexpected crashes or failures of individual containers do not take down other containers. For example, a crash in the primary SRT container would not affect the secondary SRT container, and the transcoder service would switch to using the secondary source as input to libtranscoder. And third, well-defined gRPC API boundaries between containers provide a simpler and more flexible framework compared to traditional IPC. Now that we have a pod that can perform live transcoding, let's look at how transcoder pods are deployed and managed. Each channel is assigned a Kubernetes deployment specifying one replica of the live transcoder pod. A Kubernetes deployment is a built-in resource that provides pod replacement in the event of node failure and rolling update orchestration. As a continuation of deploying and managing live transcoders, we come to the operator. Its purpose is to do the work a human managing a live transcoding service would do, but in an automated fashion. Things like install, update, and delete live transcoders, create source routes to live transcoders, apply AVR ladder configurations to live transcoders, upgrade the version of the live transcoder used for a given channel, and lastly, calculate how much CPU is required for a given transcoder at install and update time to better optimize bin packing. To go further on optimized bin packing, channels running on the streaming platform have varying resource requirements with respect to AVR ladder. Higher resolution, higher frame rate, more layers, all increase the amount of compute required to transcode in real time. Ladders can vary as well, from SD 480p30 all the way up to full HD 1080p60. To handle this, the operator uses an algorithm to estimate the CPU cores needed for a given channel's transcoder, given its AVR ladder. This, mixed with Kubernetes built-in bin packing, allows us to have heterogeneous resource allocation for pods safely running together on a given node. In this example diagram, we visualize how pods are bin packed. The blue squares represent live transcoder pods requesting various number of CPU cores, scheduled onto the 3 nodes. Each of these nodes has a maximum capacity of 96 cores, and are each well bin packed to over 90% utilization. The purple box represents some soft headroom. As more transcoder pods are scheduled in the cluster, this headroom will be taken up by those pods, and the cluster autoscaler will launch more instances to ensure the soft headroom is always available. This headroom provides space that's instantly available for newly scheduled pods due to adding more channels or replacement pods for those that were running on a failed node. So what is a real-world example of this? Well, during the NCAA March Madness basketball tournament this year, there would be varying numbers of concurrently running games throughout the opening rounds. Transcoders for each game were spun up at least an hour before tip-off, so that operators could run through their checklist and ensure the streams were ready for viewers. As each transcoder was spun up, it would use up more of this soft headroom, and the cluster would add more nodes as necessary to ensure there was always space for the next game's transcoders whenever they were to be spun up. As games ended throughout the day, the amount of soft headroom increased, and the cluster scaled in. For our customer, there was always space available to start the next transcoder for the upcoming games, and for us, We only want launched and ran nodes for as long as the customer needed transcoders running. Now, lastly, we zoom out to a single cluster view where we can see the operator interacting with channel API, source API, and the Kubernetes API in the control plane. Then in the video data plane, we have live transcoders for various channels consuming SRT and outputting ABR transcoded segments to the packaging and publishing service. With channels being assigned to clusters at channel creation time, scaling out further is as simple as adding more clusters. With that, let's review what we have been able to achieve with this architecture. We achieved premium quality, 1080p 60 output with 4K launching this quarter, all with the same original architecture. We achieved advanced features like frame-accurate SCTE-35 signaling, Nielsen, video slating, redundant sourcing, and seamless failover. In availability, incidents have been reduced by an order of magnitude from several per day to 1.8 per month. Transient failures now heal automatically. We have at least 5 nines of transcoding availability for most channels. In scalability, there's no capex to add more layers or channels. Recently, we had a customer that wanted to increase the quality of a large percentage of the channels we provide to them, from 720p to 1080p. Previously, we would have had to purchase or lease more hardware from our vendor, taking many weeks to months to be able to implement this change. Now, we simply make the requested ladder changes and the platform scales to meet the demands of the increased workload. Scaling to support more channels, higher quality profiles, or more concurrent events used to take months and now only takes minutes. And in agility, we no longer have scheduled maintenance to do code upgrades. We have biweekly transcoder version upgrades for all customers without downtime during business hours. This has freed up our development cycle, and we allowed us to iterate on our platform and provide cost-optimizing features like running on spot instances. And finally, I wanted to go over a few lessons that we learned that I felt were noteworthy. First, customers have to evolve with the platform. Our customers are used to not upgrading transcoding infrastructure very often, and when they do, it usually happens during overnight maintenance windows. Being able to perform biweekly transcoder upgrades during business hours took some convincing, and it took time for them to see that it was safe. Second, don't try to boil the ocean. This one may seem obvious. Trying to get feature parity with the previous platform before going to production would have taken years. We picked a customer with the minimum features needed and got them into production within 3 months. Then we picked the next customer, implemented the features they needed, and got them into production. We continued this process until we had all customers on the new platform. As we went along, we rewrote components of the service as needed to meet the demands of new features being implemented. And third, cloud networking is not perfect. A reliable transport is a must, even when using AWS Direct Connect with private peering. The SRT library we use provides rich flow-level statistics that we emit as metrics from every one of our SRT translation containers. These metrics include latency between sender and receiver, packets lost, packets recovered, packets arriving out of order, etc. These metrics are tagged with the channel they belong to, the host the containers are running on, the cluster the transcoder is running on, and the availability zone, to name a few. This has given us fantastic visibility into the health of traffic flowing between our data centers and the cloud. We are much more quickly able to diagnose and isolate the cause of source degradation, whether it be upstream of iStreamPlanet, isolated to a specific availability zone, isolated to a specific direct connect circuit, and so on, thanks to these metrics. And with that, I will conclude my talk. I sincerely hope you enjoyed it.
Hey everyone, we're back, and I have with me Justin Mason from iStreamPlanet. Hey Justin, thanks for joining.
Thanks for having me.
So yeah, thanks for that great presentation. It was really awesome to hear about, just a different perspective on live streaming, not the same thing as a lot of the UGC content folks that we've been talking to so far, but just, the premium stuff with the sporting events. So definitely some unique challenges there. So with that, yeah, we'll start with the audience questions here. The first one comes from Kirill in the audience. He's asking, so using UDP on ingest, you mentioned. So how do you deal with packet loss that comes with using UDP?
Sure. The SRT protocol we utilize implements a time-based buffer. And this time-based buffer is a fixed length. And so say if you had a time-based buffer of 100 milliseconds, any packet that enters that buffer will be in the buffer for 100 milliseconds. And so what basically that means is that you have up to 100 milliseconds to NAC and to request retransmits of packets from the sender. And then the sender will hopefully send you the packets that you missed or that didn't arrive. And then you recover them that way. And so with it being a fixed buffer and everything delayed the same amount of time by 100 milliseconds, it means that you're on the output side, you still get a consistent stream of data as it entered the sender, but it does give you a chance to recover the packets. So that's how we deal with packet loss.
Makes sense, makes sense. The next question is a little more broad. It's how do you generally measure system performance from a user perspective? So things like quality of service, quality of experience as the system is changing.
Sure. One thing that we, as I outlined in the talk, we have specific measurements that we've done over the couple of years, and we need consistent performance out of the product. And so we actually don't allow too many tweaks and tunes to encoding profiles. So we stick with a very good quality profile. And so all of our model is built on these profiles, and we don't really make a whole lot of changes to them so that we have deterministic performance. And so from an end user perspective, I would say the biggest difference and the biggest factor for how good something looks is really on the source, the source that's coming into us. We have a phrase we use a lot here called garbage in, garbage out. And the best quality source we get in it's going to result in the best quality output we can provide. And also, as we're changing things in the system, we have 24/7 channels that we also run in our own test environments that run identical to production using the same mechanisms. And we basically are testing on monitors and alerts for any type of performance regression, so we know if we make changes to something and it reduces performance, or some containers are running over their CPU allocation.
There, yeah. It looks like actually the beauty of live. We have a follow-up from the first question, which was about the use of UDP on ingest and packet loss. So the follow-up was 100 milliseconds might not be enough. So there must be cases when packets get completely lost. And wouldn't that eventually introduce jitter downstream in the play?
So the 100 milliseconds number I gave is just a number I pulled out of thin air. That's actually not the number we use. We use somewhere between I think around 200 to 250 milliseconds. And the protocol itself specifies they specify a recommendation of 2.5 times RTT to be your time-based buffer. And we actually go a little bit above that because we can handle a little bit more latency, and we want to ensure that we get that data. But yes, eventually, like, it is possible that you don't get all the packets and that one will be dropped. That does happen from time to time. And in those cases, since it's MPEG-2 TS, that appears as a CRC error, a CC error, continuity counter error, and which results in lost data. And in those cases, one of the things we mentioned in the talk very briefly is we have some what we call source merging, where we can recover lost data. And that's what saves us in those cases where that's one of the reasons why we receive 2 feeds at the same time, so that if one If we lose data on one feed, we can recover it from the other.
Got it. Got it. So the next question is from John Porterfield in the audience. And the question is, I take it you're using some kind of device using or supporting SRT into AWS Media Connect or an AWS Link product.
We do not use Media Connect. In our data centers, we have a device that supports SRT, and in our containers, we integrated libSRT ourselves.
Got it. Let's see. Another question here. Does your architecture assume that a single stream can be transcoded in real time on a single node?
Yes. Currently, the architecture is designed for a single transcoder to run on one node and only one node. Now, that doesn't mean that there is only that one transcoder running on that node. There are multiple transcoders running on each node, but yes, the architecture assumes that everything's running locally.
Got it. Another follow-up from Carol on the UDP question, which is, well, why use UDP if you're introducing a 250 millisecond buffer? What would you describe as the gains in that case?
The gains are that the stream will continue and move on. There's no jitter like there would be with TCP. TCP, guarantees delivery and can back up and bottleneck, and you could end up choking the transcoder if you were to use something like TCP that never gives up. But that's one of the reasons of why we use SRT, is because it will eventually give up if in the event of severe network or even momentary network loss. If we had momentary network blips for TCP, you'd have to worry about issues like especially depending if you're not using something like BBR, if you're using like a loss-based TCP congestion control algorithm, that will definitely shrink your send buffers and cause you to not be able to send data as fast. And it just introduces a lot of challenges for delivering data smoothly over TCP.
All right, thanks. I think that was our last audience question. So we have a few minutes if you had any last closing comments or thoughts based on the questions, or just wanted to say goodbye.
Let me see if there's anything else.
It's okay if not.
I don't know. I don't really have much. I really appreciate you guys having us on, though.
Absolutely.
I've really enjoyed this. This is my first talk, so if it looked like it, that's fine.
Didn't feel like it. You did a great job. So thanks again for joining us, and thanks for preparing that presentation. I think there's a lot of good discussion in the comments, so that's a good sign. So I guess, yeah, for now we'll transition next to David and Priyam from Facebook, who are going to talk about in-stream video understanding.